To understand stereochemistry, we have to understand something called chirality. And we're going to start by thinking about the fact that a chiral object, if we can call an object chiral, chiral object is one that is not superimposable on, which means congruent with, its mirror image. Okay, so let's look at that definition first, and then we'll be able to get into some molecules. So consider your hands. So hold both of your hands up as though you're pushing against a wall, and then turn them so that they're facing one another. When you have them facing one another, it's easy to see that one is a mirror image of the other one. So if you take them and then put them next to each other, so I'm going to try to draw some hands. This is terrible. I hope your hands don't look like this. Okay, so here are your hands. These are the palms. Okay, now let's flip one of them over. So the one on the left stayed the same, but we're going to turn over the one on the right. And when we do that, now we're seeing the back of that hand on the right, and those are supposed to be fingernails. Okay, if you take the one on the right, pick it up out of the page and try to put it on the one on the left, or if you try this with your actual hands, then yes, all the fingers will match up. As well as the thumb. But from your perspective, you're looking at the palm of the hand here, but the back of the hand here. So as you can imagine, this is kind of hard to explain when I can't actually show you what to do. The point here is that your hands are mirror images, but they're not superimposable. So when you place one on top of the other, not all of the features are going to match up. Okay, so those are chiral objects. So each one of your hands individually is a chiral object. And they are mirror images of one another. But what we're interested in is molecules. So we'll just extend this to say that a chiral molecule is one that's not superimposable on its mirror image. So here's a picture of a molecule. This one does happen to be chiral. And what I have done is put it on my kitchen counter, and then I got my bathroom mirror and propped the mirror up there so that the molecule is essentially looking at itself. So it's admiring itself in the mirror. Okay, so that's a pair of mirror images. One of them is strictly an image. Okay, it's not a real molecule. So then I made a model of it, and that's what we have in the next picture. So let's draw this. We have two bonds in the plane. This one is to orange. This one is to yellow. One going back, that one's to blue. And one coming forward, that one's to green. So that's the structure on the left. The structure on the right has two bonds in the plane. The bond to the blue atom is going back. The bond to the green atom is coming forward. So that's the three-dimensional drawing, or I should say the two-dimensional drawing of the three-dimensional structures that we're seeing in the left. Okay, so the next question we have is, are these superimposable mirror images? So could I pick up one of them, place it on top of the other, and have all the colors match up, all the features of each molecule match up? If that's the case, then they would be identical. But let's try it and see. Now, for all of these exercises that we're doing, and as you're trying to learn about chirality and stereochemistry, I strongly encourage you to make models. Okay, so what I did was I just picked up the structure on the right, picked it up off of the counter, moved it to the left, and tried to place it on top of the one on the right. Okay, now as we can see, they are not superimposable. So the positions of the orange atoms are matching up. The positions of the green atoms seem to match up, and the blue atoms, but the yellow atoms do not. Okay, so in this example, what we did was we picked up the right molecule, you write that differently, the molecule on the right, moved it to the left, and placed it directly on top of the molecule on the left. We did that to test for superimposability. The result here, it looks non-superimposable. The structures look to be non-superimposable on one another. However, you're not limited by that. Okay, you don't have just one move. So let's go back to our original picture. So that's what we have here. So I'm going to go ahead and draw a little mini version of this. So orange, yellow, blue, and green. That's on the left. And then orange, yellow, blue, and green. That's the one on the right. Okay, so what I'm going to do with the structure on the right now, as it turns out, just like with your hands, you don't have just one way that you can test for superimposability. You can move either structure around as in whatever ways you want to try to get it to superimpose on the other one. So you can flip it over, you can rotate it, you can flip it and rotate it. Basically anything you need to do if you have two models to try to see if they will fit together or if they will superimpose on each other, you're unlimited in the moves that you can make. So what I'm going to do now is take the structure on the right and flip it over horizontally. And that's going to give me this result. So the structure on the left, I haven't changed. I haven't done anything to it. I haven't moved it or rotated it or done anything. So that's the way it was. But the other one I flipped over. And so what that means is now our perspective is different. So now orange is still up, and the bond to the yellow is in the plane. But now the bond to the green atom is going back, and the bond to the blue atom is coming forward. So now we pick up that model, move it left, and try to place it on top. And what we see is the result on the lower left. So now the orange atoms line up, the yellow ones line up, but the green and the blue do not line up. So the structures are still non-superimposable. Okay, so we could continue doing this, and you can continue doing this if you make models of these two. And what you'll find is that you're going to be doing this for a very long time and coming to the same conclusion, is that these are not superimposable mirror images. So as such, they are a special type of stereoisomer. They're called enantiomers. So non-superimposable mirror images are called enantiomers. Now there's some things that are going to be generally true. First of all, every chiral molecule has one and only one enantiomer. Okay, so going up above, let's look at this picture where I've drawn the structures. Okay, so our original one was the one on the left. That was the one that was looking in the mirror. Okay, so It was looking in the mirror at itself. It was admiring itself. It likes its friend too. It likes its enantiomer. Anyway, it was looking in the mirror. And so this is our original structure. So we drew its mirror image, or we generated its mirror image, and then we tested for superimposability of the two structures. So what we found out was that our original structure, its mirror image is non-superimposable on it. And so that means that it's a chiral molecule. But the same thing is true for the mirror image itself. Its mirror image is our original molecule, which is not superimposable on it. And so it too is chiral. So every chiral molecule has one and only one enantiomer, which is what we saw above. And let's fine-tune this a little bit. A molecule that has one asymmetric carbon is chiral. So if you look at a structure and you identify that there's one asymmetric carbon in it, you know right away that that is a chiral molecule. So to go back to the example we were working on, in each of the structures, it's the carbon that I've just highlighted that's the asymmetric carbon. Okay, each of those carbons has 4 different things. We're representing the differences by the different colors, and so those are both asymmetric carbons. Okay, now what if you have structures that have more than one asymmetric carbon? So a molecule that has more than one asymmetric carbon may or may not be chiral. So if you have more than one asymmetric carbon in your structure, that may or may not be a chiral molecule. And we'll figure out how to look at things like that a little while later. Okay, so we know some things about the properties of chiral molecules. Now let's compare that to achiral molecules. First of all, let's think about, what does a chiral molecule have to have? What features must it have? Well, first of all, it has to be non-superimposable on its mirror image. So we saw that. And we also saw that every chiral molecule has one and only one enantiomer. So enantiomers come in pairs. You can't have a set of 3 enantiomers. And remember, the enantiomer itself is also a chiral molecule. Now, in general, a chiral molecule doesn't have to have an asymmetric carbon. But because we're starting this out, this is an introduction to the topic. For our class, the vast majority of the examples, we're going to see at least one asymmetric carbon. So that's what you should be focusing in on at this point. And then the final thing is that a chiral molecule lacks what we call internal symmetry elements. Now, the most common one, or the easiest one to see, is an internal symmetry plane. So this is the structure from the previous examples. We already know it's a chiral molecule. And so what I've done is put down some tape on my kitchen counter, and the tape is supposed to represent a plane. So imagine that there's like a sheet of glass or plastic, clear plastic or something like that, that's cutting along the edge of the tape, and that's perpendicular to the countertop. So this is going to help us to visualize a plane. So a symmetry plane means that you go from a point on one side of the plane. Let's say you go from this atom and you travel to the plane, and then you go an equal distance. And if you find an identical point, then that's a symmetry plane. But that has to be true for all the points across the plane. Okay, so what we're seeing right away is that the blue does not reflect into the orange, whatever those 2 atoms are. So this is not a symmetry plane, this orange plane. Now, it should also be noticed that you can cut atoms in half and you can cut groups in half. So for example, this green atom, that could be a hydrogen. You can cut it in half with a plane, and the left side would reflect into the right side. But the point remains that the blue atom doesn't reflect into the orange, so this is not a symmetry plane. That doesn't stop us. We'll just turn the molecule in a different way, and we'll try to see if there's another plane that would be a symmetry plane. So we do it again. In this case, it's the blue that's not reflecting into the green. We can cut the orange and the yellow in half, and the left half will reflect into the right half of each of those, but the blue atom doesn't reflect into the green. And so what we're seeing here again is that this plane, in both cases, is not a symmetry plane. Okay, so chiral molecule is non-superimposable on its mirror image. The mirror image will then be called its enantiomer. And a chiral molecule lacks internal symmetry planes. And so we just saw two examples of looking for planes in a chiral molecule, trying to determine if they were symmetry planes and seeing that they were not. So now let's turn our attention to achiral molecules. So by contrast to a chiral molecule, the term achiral means not chiral. And so an achiral molecule is superimposable on its mirror image. So here's a molecule called dichloromethane. And so I made a model of it. It's the one on the left. The hydrogens are the yellow atoms, and the blue atoms are the chlorines. I made its mirror image. That's sitting next to it on the right. And so I can pick up the mirror image, and by moving it around a little bit, place it on top of the original, and see that they are, in fact, superimposable. So the mirror image of an achiral molecule is superimposable on the original, meaning the original achiral molecule. Oh, they like each other. And so then the other thing that you would think about for an achiral molecule is that an achiral molecule does have an internal symmetry plane. So examining the plane, one of the planes in this molecule, you're going to find more than one internal symmetry plane here. Remember, we can cut the hydrogens, or whatever groups are atoms, we can cut those in half so that the left half of the atom or group reflects into the right half. And in this case, the chlorines also reflect into each other. So remember, you start at a point on one side of the plane, travel a particular distance to the plane, travel the same distance on the other side of the plane, and you should find an identical point if that's a symmetry plane. Okay, so let's finish this by looking at a couple of ways that we can draw enantiomers. You can use one of two methods. First of all, you can draw the mirror image. Now we have a little bit of practice with that in the earlier part of the video. I did an example or two of that for you. And so if we imagine, here's our mirror, then the mirror image of this guy looks like so. So you just draw the reflection of what you see. Okay, let's take a look at these two structures. Okay, the one on the left is chiral. It has one asymmetric carbon. So this is a chiral molecule, thus it will have one enantiomer. And so to draw it, we just draw the reflection of what we see, again, as if you were holding your hands next to each other. Okay, so you could always just draw the mirror image. But remember that an asymmetric carbon is a stereocenter. It's a specific example of a stereocenter. And by definition, a stereocenter is an atom at which, if you exchange two groups at that atom, you get a new stereoisomer. So to draw an enantiomer of any chiral molecule, what we can do is switch the positions of any two of the groups attached to every asymmetric carbon in the molecule. So let's work on a couple of examples of this. Let's call this first one star. And so what we'll do is we're going to switch two of the groups attached to the asymmetric carbon, which is the one that I've highlighted. So we're assuming that A and B and C and D are all different. So that highlighted carbon is asymmetric. And that's true up here as well. Okay, now it doesn't matter which two groups we switch. We can switch any two groups. So I'm going to switch B and C. So I'm going to leave A and D as they were. B started out as back, and C started out as forward. So I'm going to put B forward in the new structure and C back. So I've exchanged the positions of two of the groups at the asymmetric carbon. Okay, by doing so, I have just drawn the enantiomer of our original molecule, which is called star. But if you look at the two structures, it's not that easy to tell that those are mirror images. Okay, now you can take it on faith. I promise you that if you do it this way, you will generate the enantiomer. But if you're not convinced, then you can make models and test this out. So first of all, flip the molecule over. Okay, so what that means is what we did in the previous examples. Okay, when we were testing for superimposability, remember that I just turned the molecule over. I didn't rotate around any bonds or do anything like that. I just changed its orientation in space and thus changed the picture that I would see when I look at it. So if we flip the molecule over horizontally, then what's going to happen? A will stay the same. D is going to come over to the right. B is going to come over to the left and it's going to move back. And C is going to come forward and also move to the left. Okay, so you're just flipping this over like you were flipping a pancake. Now it's easier to see that this is, in fact, the mirror image of our original molecule star. Okay, let's do another one. Now instead of A's and B's and C's and D's, let's have actual groups. Okay, so here's a molecule that has one asymmetric carbon. So right away, because it has just one asymmetric carbon, we can conclude that this is chiral. We'll call it star as well. And so to draw its enantiomer, we could either draw the mirror image like we did up above, or switch two groups. I'm going to switch the H and the OH. But again, it doesn't matter. Any two groups. Okay, so now we get to this. Okay, so we could go through the exercise of flipping it over and then comparing to the original structure to verify that we can see in the drawings that it's the mirror image, but we know that if we flipped two of the groups, or switched two of the groups rather, at an asymmetric carbon, we have definitely generated the enantiomer. So what happens if we switch two groups again? So this time I'll flip, or exchange rather, the bromine and the methyl group. Okay, so if you switch two groups from your original molecule, you get the enantiomer. If you switch two groups again, that takes you back to the original. So now this is star. Okay, now I will leave it to you to check with models to make sure this is star. The way you would do that is to make a model of the original picture, which is this one on the left, and make a model of what we ended up with, which is this one over here, and then try to superimpose them. What you should find is that they are completely superimposable, which means that they are identical structures. Okay, let's do one more. This one has more than one asymmetric carbon. It has two. So to draw its enantiomer, remember we have to switch two groups at all the asymmetric carbons. Okay, now it's important to recognize that there's some bonds missing. Those are going to be to hydrogens in our original structure. So at the carbon that has the OH group, remember there's a bond going back, that's to hydrogen. And at the carbon that has the bromine, we have two bonds in the plane and one going back. That means that there must be one coming forward, also to a hydrogen. So if we switch two groups, that means that on the left carbon, the OH is now going back, and the H is coming forward. And on the right carbon, the bromine is going back, and the H is coming forward. Now this is an example. Our original molecule in this example is one where there's more than one asymmetric carbon. And so what I told you previously is that may or may not be chiral. So we'll learn how to tell if it is or not, but what I'll tell you for now is that it is chiral. This is a chiral molecule. And so the structure we ended up with after switching two groups at each of the asymmetric carbons is its enantiomer. And of course, the enantiomer is also a chiral molecule.